All right, so I will go on with cyclotonic associators today. And so yesterday we had a few motivation, and I will need some like operatic background, which is a bit unusual, so that I need to tell you about. So I want to introduce something that is called a operad, and it's after Thomas Wilbacher. So recall so that there's another monadal product which is symmetric on symmetric sequences. In a nice enough symmetric monadal category. And it's given as follows. So as opposed to the circle product, I write the tensor product of S and T of two symmetric sequences in arity N. That is just the sum for P plus Q being N of the tensor product of P array operation in S and Q array operation in T. And then you have to induce from the product of both of the two symmetric groups with P variable and Q variable to symmetric group with N. All right. And so the unit for this monadal structure is different from the one for the circle product. So the units for this in array N, that is, well, that's just the unit of the monadal structure of C if N is 0 and nothing else. All right. So now let O be an operad. And so the definition of a operad over O, it's a kind of operatic module, but it's not an operatic module. So is a symmetric sequence. Let's say, let's call it M, together with, first of all, a unital monoidal structure, monoid structure, sorry. For this tensor product, a right module structure. So O is a monoid for the circle product. So that's a module structure for the circle product. And that are compatible in the following sense. I basically want a diagram to commute. So we have M. We can tensor it with M circle O. We can apply the module structure, the right module structure on M. So we get to M tensor M. And then we can apply the monoid structure for the tensor product. So we go to M. Then one can check that there's a natural transformation from this tensor product with the circle product with M tensor M circle O. And there you can first apply the monoid structure and then the module structure. And we want this to commute. If you want to know about this map here, essentially that looks as follows. So you have like upstairs, you would have components which are of the type M and 0, tensor O, I don't know, K, and then tensor M, M1, tensor M, MK. I will have the tendency to like put this term on the right afterwards, but anyway, for the moment, let's write it like this. And this has a map to let's sorry. No, I wrote it completely the wrong way. That's an MK here, and these are O's. And so we just write MK tensor M M0 tensor, let's say O M1 tensor, etc. O MK. So that's just reordering, and then we just put copies of O1 tensor O1. And since all my operads are pointed, there's such a map. And that map really belongs to this thing here. Okay. If you want a description more in terms of partial composition, that goes as follows. So we have the circle I operation for I, let's say going from 1 to K. That has the following thing. So we have like MK tensor O M that goes to M K plus M minus 1. That's just the right module structure. And there's an additional partial composition, which we write circle index 0, which takes MK and M, let's say N, and it goes to M K plus N. Yes. Yeah. Yeah, basically, these ones are plugged in, this one. Yes, that's true. It is true. Well, anyway, in the end, I will always write, I take the convention from here and plug in from the right. No, it's not a commutative monad. I agree. All right. So, yeah, maybe in terms of trees, so you may want to write the elements of MK as like things like this, and basically, so the thin lines are the operatic one, and the thick one are from the operad thing. So you can plug in some operatic operation from O here, but you can also plug in some M element from M here. That is rather this operatic thing, right? So there's a kind of specific spot in which we substitute with element of M itself rather than with element of O.
All right, can I ask a question?
Yes.
So what's the relation? So I mean, monoid structure, is that the same thing as a left module structure over the associative operad?
Over what?
So you can talk about left modules over the associative operad in symmetric sequences. And is that, so
it might be, I don't know. But,
so I'm wondering whether this is, I mean, so you can talk about bimodules, so with respect to the associative operad acting on the left and O acting on the right. And my question is whether this gives the same notion.
Probably yes.
Okay. All right. Thanks.
Yeah. So let me give examples of this. It will be better. So the first example is it's something that's going to play the role of a unit somehow. So let's call M unit. So in array n, that's just the unit of the modular structure for every n. And so this unit is a moprad over operadic unit, which I defined in the first lecture, which was the monoidal unit in array 0 and 1. Okay. Yes.
Is the second operation a horizontal operadic composition facing the tree next to each other?
No, I don't think so. So no, yeah, I don't think so. So let me introduce some convention. All moprads will come equipped with a morphism from these units over the morphism of operads from unit to O. So by convention, a moprad over O, for me, it's going to be something that comes equipped with a pointing like this, which gives you a morphism of unit moprad. All right. So like the reason is because it has some consequences. First of all, it allows to again have like this deleting operation I was talking about in the first lecture. So that's to have deleting operations that decreases the array. And we also have then a morphism of symmetric sequences from O to M. Whenever you have something of that sort, you always have a morphism of symmetric sequences from O to M, which means that you can somehow see the operad inside the moprad, and that we will need at some point. All right. So here's another example. There's the operad, let's say PA index 0. So that's so in array n, that's a maximal parenthesization of sequence of the form 0, sigma 1, sigma n, where sigma is a commutation. So that's essentially parenthesized commutations, but with the frozen spot, which is the first one, which we call 0. Okay. And definitely, whenever you take, so this is a moprad over the operad of parenthesized permutations. Basically, at every spot which is not 0, you can substitute a sequence which is of the type like a parenthesized permutation. And at the spot 0, you can also do some substitution, but with something of the very same type as this one. Okay, so for instance, and that's something in the category of sets with the Cartesian monoidal structure. So for instance, typically, like you would have like this, like with the partial composition at 0, with I don't know, like 0, 3, 2, 1. What we're doing is we're inserting that guy here at the 0 spots, and then we have to renumber things. So that's going to be 0, 3, 2, 1, like this, and then 4, 5, like this. And that's what we've inserted. Okay. And the morphism from this morphism unit to this parenthesized permutation with the frozen spots, that's just given by, well, in sets, that is just in every array. That's just a point. So that's just the choice of a specific element in PA0n for every n. There's a question.
Sorry, on the right, so bracket n that you have a first bracket 0, bracket 1,
With the second one here?
No, on the right.
I'm not sure I understand. So. Oh yes, you're absolutely right. So there's a bracket here. Is that what you're saying? Thank you very much. Was there another question? No, that was the thing. Okay, so we have this pointing here. So it's basically choosing a distinguished element in PA0n for every n, and that is just given by the leftmost parenthesization of the permutation, which is where nothing is permitted. Okay. All right. There's another example. Let me call this cob, let's say 1n. So that is, so this thing will be braids on n+1 strands with the 0th one frozen. So basically, there's a general procedure. If you start from an operad and then you freeze one spot, very often you'll get an operad. So typically, let me give you an example of a braid with a frozen strand. So we have like 0, 1, 3, 2, for instance. We have this frozen strand here. I don't know, we may have like a braid like this and like this. So that's a braid where the spot 0 does not change, but the other one can be permuted via the braiding. So it's something which is a braid, but it's pure with respect to the first, well, the 0th strand. And you can check that this is a operad over cob, and it takes place in groupoids. Okay. So basically, you can substitute one of the braid from cob at any spot, except at the 0th one, you need to substitute a braid which is of the same type as this one. Yeah. Yeah, so there's probably some general procedure that you can apply to get an operad from an operad by freezing once, like the first spots. Yes. And most examples we will be seeing are of this type. But then we'll apply some more construction on them. So. And finally, you can do the same with a, like you can mix these two examples. So yes. No.
Am I right to think that, or actually that's your first operation number, let me see, this one is not
No, that's a very good question. So like, what's the array of this? This lives, so this lives in some home space of cob 1, 3, which goes from 0, 1, 3, 2 to 0, 1, 2, 3. That's our convention. Like if you look at how we define moprats, you want that when you substitute some spot which is of operatic type, you lose one arity, so you have like m plus k minus 1. But when you substitute the 0 spots, you get the sum of the array. So like and anyway, so this guy is a symmetric sequence. So the symmetric group acts on this, but it does not act on the 0 spot. So like here, you have sigma 3 acting on this, but not sigma 4. That's like P0n. That's sequences of n plus 1 guys, where that's the exact same convention.
2 plus 3.
Yeah. All right. And similarly, you can define PAB 1n in the like PAB1 is as a moprad over PAB, again in groupoids. That's just the same as with COG, except that you add parenthesizations. Okay? All right. So now I will need to consider some group actions on moprad and some semi-direct product construction. All right, so consider let's say the trivial operad, let's say in sets to simplify things. Which by this I really mean the terminal one, so that is just star, just a point in every array. Okay. And for any set G, and I'm sorry for denoting a set G, but soon it will be a group, so that's why I'm doing this. We have a moprad over the trivial operad, which I will denote star like this. So let me write it like this. So in array n, that's just G to the n. So the action will be as follows. So we have like G to the n cross point, so that's just G to the n. And when I do the circle product with at a spot I, that goes to G to the n plus m minus 1, because this point here, that's the set of m array operation. So that's this guy here, that's just star of m, right? And what is it? You just take G1, Gn to, well, G1, Gi minus 1, and then I put m copies of Gi. So it's just a partial diagonal, right? So that's for I running from 1 to n. And then I need to tell you what is the zero array operator, I mean the zeroth circle product, partial composition, sorry. And the zeroth one is as follows. So it goes from G to the N cross G to the N to G to the N plus M. And believe me or not, it's just the identity. And you can check that it does satisfy the axioms of an operad. Well, it's a fairly simple. If G is a group, then we get an operad in groups. The only thing you have to care about is that we never use any group multiplication, which is not a group morphism. It's just like diagonals and identity. So now that there's a definition. So an operad M over an operad O carries a G action if there is a morphism from G cross M to M of operads over point cross O, but that's just, again, that's the identity map. That satisfies the associativity condition for the action. So I guess I don't have to write what the associativity is. Well, yeah, let's write it. So you have like G cross M cross G. You can either first multiply in the group and then act, or first act and act again. And that should come in. Okay? Yeah, so it means concretely, it means that G to the N acts on the MRE operation of the operad, and that is compatible with these maps I've just introduced. And there's no action on the operad itself. It only acts on the operad, on the module, if you want. Yeah, that's what I had a plan to say. So this, yeah, I just said it out loud. And also, like implicitly built in, you also have that these actions are sigma n equivariant also. Yes. All right. Now I want to talk about semi-direct products. I'll talk about it in a very specific context, which is the one I'm interested in, which is the one of groupoids. So let's G be a group. And for the moment, there won't be any operad or moperad. That's general constructions about groupoids. So there's a functor from G groupoids. By this, I mean groupoids equipped with a G action to groupoids over G, by which I mean a groupoid which has a map to G, which we view as a groupoid with only one object. And this map sends a groupoid, let's say P, to the semi-direct product of P with G. And let me explain what this is. So objects of the semi-direct product are just objects of P. And for arrows, in addition to the arrows of P, we have so additional ones, which goes like this. So if you have an object P of your group weight, you can act by it via a group element. And we formally add a map like this. So that's for every G in G and every P an object of the group weight. And I need to tell you how these maps interact with the original map that we have in our group weights. So first of all, how do they interact together? So basically, that's group multiplication. So that with the following rules. So if you compose, let's say G acting on H acting on P, there's a map G that goes to HP, and there's a map H that goes to P. This composition, as you can expect, it's just the map that goes from GH acting on P, indexed by GH, going to P. Okay? So that's just group multiplication. And then there's the semi-direct product part, which essentially tells you that if you start from G times P, you go to P via G, then you have any map between the two objects, P and Q, and then you act by G inverse, and that takes you back to G times Q, because I'm just using the fact, that's not right, the fact that Q, it's G inverse times G times Q, right? And this is equal to just the action of G on F. So you have a map from GP to GQ, which is given by G acting on F. And we just want this to be true. If you want to write it shortly, it just tells you that G, F, G inverse, that's just G acting on F. Okay, that's just the semi-direct product thing, usual. All right. This is a functor, and this functor, it has a left adjoint. That I want to describe for you. So this left adjoint, let's write it. It will send, let's say, it will send a map phi, let's say from P to G, to something that I'm going to call G of phi. So let's describe this now. It's a, well, it's a left adjoint, so it's going to be a free construction. Yeah, is it the semi-direct product of the group weight with the action group weight? I'm not quite sure about this. Yeah, and also like you have an action group weight if you have a group weight acting on a set, and here we're acting on a group weight itself, so I wouldn't know how to express the action group weight. Okay, so what are the objects of G of phi? This is just the free G set generated by the object of P. So that's G cross object of P. And a morphism from a pair G, let's say X to H, Y in G of phi. What is it? It is a morphism F from X to Y that is such that, well, if you act on the image of F by G, you get H. Okay, so somehow it just tells you that phi of F controls the difference between G and H. Okay, the typical example of such a thing, let's take, so that's a group example. So we have Bn, it's a group weighted with one object, it's a group. And we have sigma n. That's the group weight cub n, basically. It's the symmetry group, yes. Sigma n is a symmetry group. So there's a morphism of group from the Braid group to the symmetry group, which just remember the underlying permutation. And when we do this construction, we recover cub n as a group weight. Yes? Mm-hmm. Yes. Yes. Oh, like that selects these things. Yeah, sorry, I should have said that. Yeah, so it sends every object to the point, and every map. So any map is going to be a sequence of either map of group type and map of this type, and it is sent to the, like, you forget about the map of this type. Yeah, you take one and then you send the rest to the product. And this relation guarantees that you're not, it's well defined, because when you put G and G inverse, then it cancels out, you get a map of this type here. Yeah, thank you for the question. I should have said that. Okay, just a remark. For every object in P, the automorphism group of this G of phi at any pair GP, where G, and for every element of the group, that is, so that's going to be a group, and this group is the kernel of the map from the automorphism group in P of the object P to G. That's basically because of this relation here. So if you want an automorphism, you need to have G on both sides. So the phi of F should be 1. So that gives us a way. So yeah, all this is compatible with a symmetric model structure on group weights. So you can do all this for Moprads, and that gives you a way to go from Moprads over G underline, which was this Moprad defined after, using a group, to Moprads with a G action. So that gives a procedure taking a Moprad over G to a Moprad with a G action. Well, without underline, because Moprad with a G action is something that on which G underline acts. And the example of this, which will be useful for us, it's, so we're taking cub 1. It has a morphism to Z over NZ underline, which is given as follows. basically, so in array n, so it goes to z over nz to the n, and it counts the number of times the ith strand go over the 0th one. So it's number of loops of the ith strand. So that's the ith component of this map that does this around the 0th one. And it does this modulo n. Yes? Yeah, so we started from a group read which is over G. So it gets a map to G. So every morphism in my group reads is sent to a group element in G. So in particular, any automorphism is sent to G, and because that's a morphism of group read, this thing is a morphism of groups. All right, so for instance, the convention will be that if we have like this, 0, 1, let's say 2 and 3. So that is sent to, I guess, 1, 0, 0. So the strand number 1 goes around the strand number 0 once. And then the other one are not braided with 0, so they don't make any loop with 0, so that's 0. Okay? And the convention is that, there's a plus sign when you go when you overcross and a minus sign when you undercross. So the convention is this one is sent to 1. All right. So when yes, don't be sorry.
The strand number 1 can go over 0 more than n.
It can.
Okay.
It can go over 0 more than n times, but just we count modulo n.
Okay.
That's just the rule that we choose. All right, so if we apply our construction to this, we get something which we call cob n, which is G of this map, cob 1 to Z over NZ. And that's the, these are braids, which are colored by Z mod NZ. So typically objects of, let's say, cob to the n, little n, are permutations. Well, let me keep the 0. So it's still the same thing as the object of cob n, but additionally, they come with a labeling. Gamma 1, gamma n, where gamma I is inside Z mod NZ, and every gamma I is the color associated to the strand number I. Okay. Like the way we write this, let's say like 0, 2, 1, 3. And we put a little index by the corresponding element of the group associated with the strand. So the whole idea of this, which it's something I didn't talk about, but let me just make a remark here. If you remember, so the braid group is the fundamental group of the configuration space of points, well, the pure braid group. is a fundamental group of the configuration space of points in the plane. And typically what we're doing here, we're taking the plane minus the origin. We're taking the covering of this by so that's the map that's in Z to Z to the N. So that's a Z mod NZ covering. Okay. So once you have this, you also have a map from the configuration space of points on this punctured plane, like you have N points to the same thing. That's now a Z mod NZ to the N covering. And once you've fixed a label permutation, the automorphism group of this object in this operating group weights, what are they? They're exactly the fundamental group of the configuration space of points upstairs which do not coincide downstairs. So you don't allow, like, two elements could be on a different sheet of the covering, but they're not allowed to collide downstairs. And if you compactify correctly, you get this you get this parenthesized thing for the maximal degeneration points, but you may have things that collide downstairs but are on different sheets upstairs. And these labeling are exactly there to control this. So that sometimes just after we'll have parenthesization, and when you have parentheses, it means that point Z2 and Z1 are not necessarily close to each other, but their images downstairs are close to each other, and this label tells you on which sheet of the covering every guy is. Okay, so so similarly, we have PABN. Which is again defined as G of PAB1 going to Z mod NZ, which is the exact same map when you forget about the parentheses. And this is the guy that's just like PAB that can be identified with the fundamental group weight of some compactified, let's say, I'll call them twisted configuration space. And by twisted configuration space, I mean really that you have a covering, you're looking at configuration of points upstairs that do not, where every pair of points cannot collide downstairs. Let me describe some distinguished morphisms in PABN. So in PAB, and in RD2, we have the following one. So we have like something that we call E, which you can also write E1 index 0, just to remember on what object where this arrow starts. So that's an arrow in PABN. And you depict it like this. So that's the one I wrote just before. So you have 0, and you have 0 index 1. And like, watch out that, like, be careful that when you go around like this, it changes that object here, because we've seen that typically when you go around the point, you go to the generator of the cyclic group. So that's now downstairs, you get a 1 indexed by 1. And the other distinguished morphism is in PAB and 3. And that's the usual associativity. So that's 0, 1, 0, 2, 0. And we denote it psi, and sometimes to emphasize where it sits, psi 1 index, like 0, 1 index 0, and 2 index 0. Yes? Yes. Oh, sorry, you're absolutely right. Thank you. That's PABN 1 and that's PABN 2. Thank you very much. Yes. Yeah, I should have said that. Yeah, I don't know if I said it and didn't write it or even didn't say it. But this is the Mokorad over Pog, and this is a Mokorad over PAB. And really, like, if you want to understand, like, very concretely the Mokorad structure, so basically what happened is that on a strand of that type here, you can substitute a braid or a parenthesized braid, and basically you just reindex everything by the same index that you have here. So if there was a 0 here, all the new strand will have a 0. And you can substitute there as well by a braid of that specific type, and then here you just keep the same indexing. All right. Now this Mokorad PABN has a nice presentation. Well, it's not as nice as PAB, but it's nice. Can you repeat the question? Sorry. Yeah. Yeah, you have to like, no, the point is that the operad PAB does not have labels. So when you substitute, let's say at spot 2, a braid from PAB, it comes with no label, and all these non-labeled strands, you give them the same label as where you substituted it. Other questions?
Yes.
Yeah. Yeah, so the configuration space, so the twisted configuration space, I should write this. So what is this? That's a collection of points Z1, Zn into C star, such that for every pair of points, they do not collide downstairs. It means that for every I different from j, Zi to the n is different from Zj to the n. Okay? So, which is a stronger condition than not being equal. Because, yeah, Zi and Zj could be different, but their nth power could be, could be the same. A stronger condition. Yeah. Like if there was an equality, that would be weaker, but there's a. Yeah, so that's so like this configuration space, you can view them as complement of hyperplane arrangements. And this is another example of a complement of an hyperplane arrangement where you choose different hyperplanes. Sorry? In C to some power, yes. All right, so let me give you a presentation by generators in relation somehow of PABN. Well, let me write gamma for Z mod NZ just for convenience. So the theorem which we proved with Martin Gonzalez is that, yeah, so there's a lot to say. So as a PAB moprad, which means a moprad over PAB, in groupoids with a gamma action. So what I'm about to say is that, like, in the category of PAB moprad in groupoids with a gamma action having this and that, the object is initial. So it satisfies the universal property. And having PA0 as PA moprad of objects. PABN is generated by E and psi with the following relations. All right. First relation is the following. So it's not surprising. It's like when we remove a strand, we want. So notice that you cannot remove the 0th strand. That's something that you cannot do with the operadic axioms. But if you remove one of the operatic strands, we want this to be the identity. If you look at this psi here, so I should have written a thick strand here. If we remove one of these two strands, we get just the identity. Then there's a kind of pentagon equation. People call this the mixed pentagon because it mixes psi and phi. So we have psi. So it's exactly the same equation as we always write. Except that at the very last part, there's a phi. Okay, so what does this mean? Every time you, like, for example, when you double, so when there's no comma between two indices, it just means that we've done some operatic composition. So we've inserted identity of two strands via the partial composition at that spot here. So it means that we have doubled one strand. We can also do this at the 0th spot using the partial composition at 0. And finally, there's this phi, which lives in O, in the operad and not in the moprad a priori. And what we're doing here is we're using the convention that we had in the beginning. When I say moprad, I mean something which is pointed by this map unit, which allows in particular to view any element of the operad in the moprad. That's basically, in terms of braids, that's just you have a braid with no 0 strand, and you just add a 0 strand on the left, and you put the leftmost parenthesization with that. Okay? So we have this equation, and like seeing that it's satisfied, it's like the usual thing, except that you have to distinguish between the zero strand and the others. Now we have the difficult equations. And I'll draw pictures to explain them. Because like when you see them for the first time, so I'll write the equation and then I'll draw the pictures. So there's first equation, second. The third equation is it's psi, and then you apply E, and then psi inverse. And this should be the same thing as applying E twice. So let me explain this with a picture, because otherwise it's a bit, it can be a bit confusing. So what happens on the left? So we start from something which is parenthesized like this. So we have 0, we have 1, which is labeled by 0, and we have 2, which is labeled by 0. We first apply psi, so that guy travels here. And then we apply E to 0 and to the group 1 and 2 together. So it means that we take these two things together and make them turn around the zero strand. So if you draw the picture, that gives something. Yeah, I'm sure I'm gonna do something wrong. So there's something about framing which I don't want to mention at all. So like when you turn, it does like this. And they should do this. Is that correct? So this go under and under. Sorry? Yeah, it's not that they cross, like, imagine that this thing is a kind of ribbon and you're making it turn around the point. So it has to twist when you turn around, okay? And it's telling you that this is the same as doing what? Like making 1 turning around 0 and then making 2 turning around 0. So that's this. And then make it, 2 turn around like these two things. So then you have this. And you can see that's like if you stretch this here and move them apart, you get exactly these two things. Like here we've applied E so that the index max change. And here, when you first apply E on the well, here that's like this. Oh, I forgot. Yeah, I forgot the psi inverse to get back here. Sorry. So I just want to point out that when you do a first turn here, the label of this guy is now 1, and the label of this guy is still 0. But when this guy turns around, the final label is 1 and 1 here as well. Okay. So that's the kind of topological explanation for, or the drawing explanation for this relation here. And finally, there's the last relation. Which tells you what happens when you apply E to the group 0, 1, and then 2. So when you make turn 2 around the pair 0, 1. All right, right? And that makes the following relation. There's a psi, then there's an R, then there's a psi inverse, then there's an E, and then there's again psi R psi. 0, 2 index 1, 1 index 0. Then there's R 2 1 1 0. And then there's psi 0, 0, 1. Yeah. So let's draw a picture. So the first one is super easy. That's just this. Okay. And then we have 0, 1, 0, and 2 indexed by 1. And we want to decompose this in the following way. And basically, it's just when you turn around two guys, you first cross the first one, turn around the second one, and then cross again. But you have to insert psi to like reorder the parentheses. That's just this. So shortly, that's as follows. So we have this, and then you travel, that's a psi, and then you braid these two, and then you travel back, so that's psi R, psi inverse, and then you go around the 0 strand, and you do the same game. Psi, crossing, psi inverse to get back in the original position. So that, like, the first is a psi, this is an R, this is a psi inverse, this is the E02. But now, this guy is now labeled by 1 because it made a 1 turn around 0. So that's why, starting from here, whenever we have applied the E, all the index of 2 are always these ones, right? Because we changed the sheet in the configuration space somehow. And here, there's again an R, a psi, an R, and a psi. And that's essentially this equation.
And you can implement the label with the
Yes, because because it's a presentation for a PAV operating group with a gamma action. So you get a lot of relations that you can deduce from all these ones by acting by elements of gamma to the n. Oh, this one, it appears in two relations. Yes, and they're in the, you cannot deduce one from the other. That was another question. Yes. Phi, it's the associator. So it's a PAV operad. So it's an operad over PAV.
Okay.
PAV is this operad that we discussed yesterday or the day before yesterday. And in there, you have a phi. Just similarly, you have an R. It also comes from the operad PAV. Exactly. Yes. Other questions? So, this is the point where I will start waving hands because I don't have time to like be very precise. So you can already define like at this point you can define as the automorphism group of like, yeah, that's complicated to write. So that's an automorphism group of something which is a pair. So let me write like mop groupoids gamma. And by this I mean the category of pairs an operad, a moprad over it, with a gamma action on the operad, on the moprad. So that's gamma equivalent automorphisms, which are the identity on objects between like of the pair PAB and PABM. So you can define the cyclotomic Grothendieck-Teichmuller group that way, and like the theorem is that it coincides with Enrique's definition, which I'm not going to like give you in full details, just because GT this GT is a bit complicated to write. Yes, that's that's also due to Martin Gonzalez and myself. Oh, okay. Hi. Sorry. So plus means there are the identity on objects. In this, it's so you should consider the category of pairs an operad, a moprad over this operad, together with a gamma action on the moprad. That's like a kind of compact notation for what I just said. All right. Yeah, you could actually put the gamma here to mean like the gamma invariant element of this automorphism group. There's so one thing before I continue, there's a small caveat here, is that in Enrique's definition there's a subgroup. It's actually the same thing as a subgroup of Enrique's group. And if you want to have the full group, you should allow things not to be the identity on object, but given by relabeling, like identity on the underlying parenthesized permutation, but relabeling of the label, and then you get exactly what Enrique has. But that's a small subtlety. So what I want to discuss right now is like infinitesimal cyclotomic braids, or cyclotomic chord diagrams, if you want. I don't have much time to give like details, just because the Lie algebras have like a perfectly fine presentation by generator generation. It's just like there's a lot of relations to write. So let me try to explain it. First of all, one can define, let's see, you can define this GPACD gamma of K as the associated graded of PAB gamma. That's a pluripotently complete. Oh yes, sorry. If I want the pluripotent version, I need to take pluripotent completion everywhere. So the pluripotent completion comes with a natural filtration on it, and you can view this PACD gamma as the associated graded of it. It has a very explicit descriptions in terms of chord diagrams. So I don't want to give the full definition of these chord diagrams. I just want to give you a taste of how they look like. So these cyclotomic chord diagrams, they have, additionally to the usual chord diagram I mentioned yesterday, and maybe the day before yesterday, they have something of that sort. So you have a distinguished you have this distinguished strand 0, and then there's a strand, let's say 1, and you can label these strands by an element of the group Z over NZ. Basically, you add this, and then by conjugating with such an element, you get new chords. So typically, like using this, you can have like T12 gamma, which is going to be, I don't know, you have 0, you have 1, you have 2 here, you have your chord, which is, that would be just T12 0. And now you have T12 gamma, where you just conjugate on the first strand by, yeah, that's conjugation, but my group is like Z mod and Z, it's additive, so that's gamma minus gamma. And by convention, it is the same as 0, 1, 2, and then you put first minus gamma here and gamma there, right? So let me put some index here as well. And in my, yeah, so here that would be 1 index 0, and that would be 1 index gamma. So the idea is that the difference of indices between the top and the bottom is just the sum of the labeling in the middle. So here, because it's gamma minus gamma, it doesn't change. Same here. But we all know things not to change the labeling in the end. If you look at the sub-Lie algebra, that corresponds to those diagrams which start with all label index by 0 and end with all label index by 0. Namely, it means that on every strand, the sum of the labeling is 0. Then you get a Lie algebra. So like if the sum of labeling on each strand is 0, and all labels on top are 0 as well, then what we get is the universal enveloping algebra of some Lie algebra, which we call Tn gamma. And this Lie algebra is generated by things of the type T0i or Tij gamma. And that's exactly the holonomy Lie algebra of these twisted configuration spaces. So it really doesn't come from nowhere. I mean, it's related to the geometry. So let me just describe T2 gamma for you, because it's the only player I need to state to describe cyclotomic associators.
Your Lie algebras, those U algebras, are your configuration spaces formal?
Yeah, I don't know actually.
Alexander, I give you here.
Yeah, so like, yeah, I should say that like with some work, you can define some PACD gamma K, or well, that's which is an operator in these categories enriched over coalgebra, and it's an annullling groupoid. It's the associated graded. So it's an operad over GPACD with a gamma action again. So, and typically the gamma action is as follows. So when you act on a Tij alpha, let's say, if you act on the ith strand, it just adds to the labeling, and if you act on the second on the J strand, so on the second one, you get a minus instead. That's just again relabeling. So let me describe like T2 gamma for you. It's actually it's a 3D algebra generated by, well, it's not quite free. It's like we have T01, T02, and T12 alpha with alpha running from 0 to n minus 1. And modeled out by the relation that's T01 plus T02 plus sum over alpha T12 alpha being central. Okay. So in particular, T2 gamma modeled out by its center. That is really a 3D algebra. And let's pick the generator to be T01 and T12 alpha. Okay, so if there was no group, that's this thing that we have seen already. That's so T2 gamma for gamma, the trivial group, that actually corresponds to T3 because of this shifting in the array, in the story about usual associators. And we know that's a real algebra generated by T01, T02, and T12, which has a central element, which is T01, which is the sum of the generators. So that's completely parallel to this story. Yes, there's a question. Yeah, in T3, it exactly tells you that the yes. Let's see.
It's a linear relation.
No, being central, it's also a quadratic relation. Because like yes, it's T01 plus T12 plus T02. Let's say bracket with T01 is 0. But then this always commutes with itself, so that's one of the Drinfeld-Coulomb relation, and yeah. So that's, yeah, for T3, you can rephrase it as saying that's the sum of like all the generators is central. Okay, and then the theorem is the following. So, and this, I mean, the theorem is really a consequence of the presentation by generators and relation of PAB gamma, or PAB n, sorry. So there is a one-to-one correspondence between elements of, again, isomorphisms in moprads in groupoids from the pair PAB gamma to the pair PACD or GPACD, GPACD gamma, which are gamma equivariants. So that's these are isomorphisms that are the identity on object between, in the category of pairs an operad and a moprad over it in groupoids, which are gamma equivalent, which are equipped with a gamma action, and we ask the automorphism to be the isomorphism to be gamma equivariant. Okay, so there's a one-to-one correspondence between elements of this group of this torsor and triples lambda phi psi with lambda an invertible element phi such that, well, no, sorry, I should say like lambda phi is an associator in the sense of Drinfeld, and psi belongs to this free algebra generated by T01 and T12 alpha with alpha going from 0 to n minus 1. Being group-like and such that two relations are satisfied. One of them is the pentagon, so like psi 0, 1, 2, 3. Psi 0, 1, 2, 3 equal I don't need to put labels here because like it just lives in here and we have like this insertion to products and nothing, I mean, no, there's no relabeling here because there's only psi's and phi's, okay? And the second relation is a bit more complicated. So it's exponential lambda t 0, 1 over n times psi 0, 1, 2 times exponential lambda t 1, 2 over 2, and this t 1, 2, 0, psi 0, 2, 1 inverse. Exponential lambda, sorry, T02 over n. And then, like, here we should act by something. So there's 0, 1 acting on the whole thing, which is the exact same thing as here. So that's psi 0 to 1 exponential lambda t 1, 2 over 2 and psi 0, 1, 2 inverse. And this should be equal to 1 inside T2 gamma modulo its center. So that's, yeah, so this relation is a consequence of one of the last two relations that I wrote in the presentation. There's a small miracle that appears here is that one of the last two relations disappears. But it's actually in the proof it's hidden that, yeah, there was the same thing in the associator story, that you can always write the associator in terms of T0, like in terms of T12 and T23, and you can like get rid of T13. And there's an argument for that. And here there's the same miracle that psi can be expressed only in terms of T01 and T12 alpha, and you can remove, like you can get rid of T02. And actually, like the relation that is not on the board, you can use it to actually prove that. So it seems that it's not used, but it's really used in the proof. Yeah, so let me finally, yeah, there's two things I want to mention. So first of all, this description of like cyclotonic chord diagrams, that's due to, I mean, the algebra like Tn gammas were defined by Enriquez, but the presentation using chord diagrams, that's due to Adrien Brochier. And he used it for studying some certain link invariants in handle bodies. And yeah, I should also mention that here in this story, so there's this is a torsor over the automorphism group of the first guy here. And in his paper, Benjamin Enriquez, he proves that this second description is also a torsor over some group. And like the real theorem is that not only you have like bijective correspondence, but all the group structure and the torsor structure, they coincide both like with the operadic presentation and with the explicit presentation using a formula. Yeah, I'm sorry that I didn't have time to talk about the elliptic case, but the long story short is that it works the same. So like in the elliptic case, you start with a torus. And well, the good operatic notion there is just an operatic module in the usual sense, no operad. There's no additional strands to work with a different substitution. And you can define analogs of like PAB and PACD in the elliptic case. And you run the whole machinery. And when you try to compute what these things are explicitly, they exactly coincide with the elliptic associators and Grothendieck-Schneller group that Benjamin Henriques has defined. Okay. Yeah. True. That's a, thank you, Martin. That's a very good point. Yeah, that's a very good point. So, like, all this story is not void. Benjamin Henriques proved that that there is some series that satisfies these equations, and to prove it, he used the same strategy as Drinfeld. He exhibited a differential equation, and he computed its monodromy, and then computing the monodromy along certain loops gives you the relation that you have here. And so that proves that it's non-empty over C. And then there's an argument involving the fact that it's a torsor that allows you to descend and to go over Q. Thank you.
Can you mention open problems in the PA?
So yeah, there's a lot of open problems in this area. So going in different directions. So there's one direction which I didn't talk about, or almost didn't talk about. It's the relation with number theory and motifs. And there's a lot of conjectures by Goncharov about the size of the Grothendieck-Schneller Lie algebra and the version, the cyclotomic version. Yeah, so like even in the rational case, like non-cyclotomic case, even for Drinfeld associators, there's still this question: is the Grothendieck-Schneller Lie algebra a free Lie algebra? I think like in a more operatic direction, there's still the question of so Martin Gonzalez he came up with a definition of what are associators in higher genus using a framed version of PAB on surfaces. He also gave a description of them by typically by general integration. So you can also define what an associator is. At this point, it's not known if the torsor of associators in higher genus, as it is defined by Martin, if it's non-empty. The essential thing is that there is a Kniznik-Zamolodchikov of connection in higher genus, but it's for the non-framed version. So you would need to upgrade this to allow little tangent vectors, and then compute its monodromy and show that it satisfies what you want. Yeah, I think there's also something else which I think would be great, but maybe it's done in some way by some recent work, and I don't remember the name of the person who did that. But so the way the proof of existence of associators go, it's a bit weird because it really uses the intuition from operads, but the Kniznik-Zamolodchikov connection itself, it's quite not compatible with the operatic structure. There's all this theory of asymptotic zones, and what you can do is concretely you look at there's two equations to check, and it's in low arity, and you check them by using you get intuition from operads, but you don't use operad at all. And that would be interesting to find a proof of existence of associator that really uses some connection or some construction from algebraic geometry, which is in some way compatible with operads. Yeah, sorry, I'm in the middle of the two things. I think there is some work that that promotes the little disk operad to the algebraic setting. There's this formal little disk operad. I don't remember the name of. Oh, yeah. No, Dimitri Ventrov, not Arkady. Yeah. And I think, like, I've not read the papers, but I think he has something that roughly does what I would hope for, but I don't know. I haven't read it carefully, so.
Control the symmetry of the solution is already
Mhm.
higher blue act on the solutions of the volume line. I made the connection between.
Yeah. So right now, so there's the story is that like you can go from associators to solution of the Cauchy-Warvan problem. Now we're starting to view things like associators in higher genus. There's also a higher genus Cauchy-Warvan problem. I don't think there's a direct map at this point that goes from higher genus associators to higher genus solution of the higher genus Cauchy-Warvan problem. But there's still this thing that's like for the Cauchy-Warvan problem, you can show that if you have a solution in genus 0, you get a solution in all genera. And similarly, oh, okay. Yeah, but okay, that's true. But there's also something that, like for associators, if you have an associator in genus 0, you can actually find a solution of you can find an elliptic associator from this. And I think Adrien Brochier has a strategy to show that starting from an associator in genus 0, you should be able to find associators in all genera. But at this point, like there's no direct connection from higher genus associators to solution to the higher genus Cauchy-Warvan problem. The solution of like the elliptic associators that you can define using a Drinfeld associator, that's the one you get when you degenerate your elliptic curve when you send the modulus to I infinity, basically. So what we did with Benjamin Riquez and Pavel Tingoff, we defined a Knisnik-Zamolodchikov equation in genus 1, like taking formula from physicists and changing them a bit. And so the fun point is that it depends on the complex structure on the torus. So it depends on an elliptic curve. So for every elliptic curve, you get a solution. And it turns out that when you send the modulus to I infinity, the solution you get is completely expressible in terms of the genus 0 associator itself. Are there more questions?
Everybody's saying thank you very much.
Great.
One more question? Sure, Damien is going to leave. That's a fast talk. Okay, so let's end Damien again for a break.